So this is modern day right here, right? See these little dots? These are galaxies. Now, if you go back in time, you find that the universe was smaller in the past. So we look around the universe and we see galaxies that are getting further and further away from us. It seems that the universe itself is expanding. And if you were to play the movie backwards, you realize that the universe is contracting through time in the past. And what you get is this model where the universe gets denser, 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 hotter, 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 until you get the singularity right here. And this singularity is where all of our understanding about physics stops. That's the end of our knowledge. It's not the end of the universe. It's the end of our knowledge. And so, based on the physics that we look at, that we understand, we can understand what this time was like right here, right? The very, very seconds and minutes and hours and years right after the Big Bang, the rapid inflation, right? So we infer based on physics, Einstein's laws, right? Einstein's understanding of relativity. We calculate what happened here. So what happened there? Well, when we look around with telescopes, we see lots of microwave radiation, lots of light. Now, we can't see it with our eyes, but it's affecting us right now. In fact, there's radiation from the Big Bang moving through your body right now. It's all around us in 360 degrees. The light from the Big Bang is all around us. And we discovered this maybe 70 years ago. It's called the cosmic microwave background. And it's radiation from the Big Bang itself, right? From this very rapid expansion itself, shortly after the Big Bang. And this is what this is, right? If you notice those pictures of those weird pictures, the blue, yellow pictures, that's what that is right here. It's the light that was able to escape in the early universe, the first light. That light has, since 13.8 billion years ago, been moving across the universe at the speed of light. And so when we look at that radiation out in the universe, we're looking back in time. So in a sense, this is like a baby picture of the universe. And we can find that if you crunch the numbers, the universe in its entirety was, as we know it, all the galaxies, all of your atoms, everything in the universe, stars and galaxies, were all condensed into this one area, this one volume, the size of a fruit. The entire universe, the size of a fruit. So you can imagine how much denser it was, how much more hotter it was than today's universe. And so that's what we're doing, right? We're compressing it all into a fruit-sized object. And you notice that the temperatures are just extreme. The temperatures are so hot at the Big Bang that there were no laws of physics that were distinguishable from one another. They were all essentially the same thing. It's called a superforce. And it was so hot that the physics we understand today just breaks down. And it took time for the universe to cool down. Not a superfluid. Not a superfluid. This is beyond a superfluid, right? This is like 10 to the 30th degrees. Even the Higgs field doesn't apply. So not even matter has mass. Nothing even has mass yet. Okay? However, as the universe inflates, like a balloon essentially, right? The universe starts to inflate very rapidly. And you get clumping of matter. You get cold enough temperatures for atoms to form, for very small subatomic particles to coalesce and precipitate. And you get dark matter as well. Dark matter was very important for our early universe and shaping the way it is today. So rapid inflation occurs, and you have atoms begin to form. They start precipitating. Now, these particles were once rapidly moving, so they couldn't, because it was so hot, the particles couldn't form atoms. But as the universe cooled down, the particles began to form atoms. And this is called the quark-gluon plasma, right? Quarks and gluons, the stuff that makes up atoms. And the first atomic nuclei, the first neutrons, began about 3 minutes after the Big Bang. Okay? However, it took about another 400,000 years for the first light to be emitted. Remember the CMB from before? It took 400,000 years for that to happen, because that's when some of the first atoms formed. The first atoms, the neutrons, took a hold of the electrons and protons and formed atomic nuclei in atoms. And now the light could escape, because before the light was being trapped between the particles, right? The particles were trapping them inside. They couldn't get out. But they escaped after atoms formed. Now, that's what we see. So we can literally see the Big Bang and how it was. And if you notice, this is the picture of the microwave radiation. This is what we see all across the universe. This is what you see if you just were to look out in the night sky, look at the darkness. You would see if you could see microwave radiation, you would see all these little dots of light everywhere around you. And you notice that it's fairly uniform. It's fairly, symmetrical. It's not too, chaotic. And that's because inflation was what caused this to happen. Inflation ballooned the universe very quickly, and it allowed the universe to conserve its uniformity. Now, the light, however, stretched. Now, this is not microwave radiation. This light was much higher in frequency. It was probably UV or X-ray. But as the light moves across the universe, it stretches with space. And now what we see today is the microwave radiation that came from the Big Bang. But in the first 100 million years, the universe was fairly dark. There were no stars yet. Stars hadn't formed yet. The universe was black, dark. It's just dark matter. That's it. You can't see it. But after time, what you have are clouds begin to coalesce, right? Clouds of hydrogen and helium. These clouds were made of the very simple atoms that were able to form at the Big Bang. That's what formed at the Big Bang. Hydrogen, helium, and some lithium and other trace elements, but mostly hydrogen and helium. And that's key because those are very late elements that can form stars very easily. They form stars. They get very big and massive as you have these clouds. They coalesce together because of gravity. They start forming a disc-shaped object. Why? Because there's something called angular momentum. And if you notice, if you're spinning like this with your arms out, if you notice you pull your arms in a little bit, you actually go faster. And that's what's happening here. You have a big dust cloud that, because of gravity, there's a central gravitational object. And it's allowing for this gas cloud to form around it. But over time, as more stuff collects towards the center, it starts to get faster and faster, and it forms a disk, a protoplanetary disk. And that's how stars are born. This is how stars begin. And you notice that once enough material gets in the center, it forms a star. Why? How could it form a star? Well, hydrogen and helium. It turns out that with enough pressure, because they're so squeezed, imagine the core of this star. Imagine a core of that gas cloud. And all that gas and pressure, we're talking millions and millions and millions of tons of hydrogen and helium. Imagine all that pressure. How fast those molecules are moving, jiggling in the center of that, because that's what essentially temperature is. Temperature is how fast molecules move. Now, in the cores of these stars, the pressures are so immense, and the molecular movement is so high that sometimes the atoms can smash together and fuse together. Those two hydrogen atoms can fuse together, and they can form a helium atom. And they can spit out energy in that process, in that nuclear fusion reaction. So essentially what's happening is nuclear fusion in the star. On a very simple, in a very simple way of putting it, the fusion of atoms happens, energy gets spit out in the form of light. And now light pushes outwards into space, while gravity is keeping the star intact. Right? So there's a balance, there's an equilibrium that happens between the gravity pushing or pulling the star in and the light from the inside pushing outwards. And you get a stable star. Now, these stars, in their childhoods, they are very chaotic. They're crazy. And what happens is they like to spit out energy in the form of X-rays or other rays that push material out. But let's get into this real quick. Once you have enough of these stars, you get galaxies. And you can see here, dark matter is what seeded the first galaxies. Because all throughout the universe, we have clumps and clumps of dark matter that we can't see with our eyes, but they're there, and they have a gravitational effect on stars around it, right? So all around the universe, we see dark matter. And they're like sinks that sink the regular matter, the baryonic matter that we're made of, towards the center of that dark matter. And you get galaxies and stars and clusters of stars. So that's how the shape of the universe happened. Dark matter shaped it. And so now we have stars and galaxies. And in our galaxy, the Milky Way, ours is one of hundreds of billions of galaxies out there, by the way. And that's just what we see with our telescopes. There could be way more galaxies out there. There could be 1 trillion, 2 trillion, 10 trillion. But let's dive into a little region of the Milky Way. We see one particular star system, one particular planetary system form. Right? Remember those planetary discs I was talking about? That's how our solar system began. So we have a spinning disk. We have a star in the center. Angular momentum keeps the planetary disk together, spinning in a disk, much more uniform. Stellar fusion occurs. Hi. You have atomic fusion occur as well inside the core of the star, creating energy and light, and a shock wave in the star's adolescence. A shock wave, push material outwards, right? So all the material from here is what we're made of. We are made of the remnants of the debris from planetary formation. And so right now it's all gas, right? So, gas and ice particles and little fine rock particles and dust. But it's being pushed out from the star. And it gets colder. So as it gets colder, it starts to form larger rocks. These rocks collect together due to gravity. They form little, rubble. And that rubble turns into larger rocks and larger rocks. It's like a snowball rolling down a hill. It just gets larger and larger, right? You see it collecting more and more material with gravity. As it collects more stuff, it collects more gravity. The more gravity it has, the larger it becomes. And you get a protoplanet. You get a very molten planet like this. You see, you get enough of these rocks hitting, smashing together, they just got to get hot, right? And our early Earth was made of just rock. It's just molten rock, and it was liquidy, actually. It was molten. And this was about 4.5 billion years ago when the Earth formed. But it was still being bombarded by rocks for millions of years. Bombarded by rocks that make up our mantle and our crust. And the Earth eventually forms and cools down over time. After heavy bombardment stopped, actually, that's a good reminder that the moon, all right, how did the moon form? Well, the moon was formed by a large, Mars-sized planet smashing into Earth. If you noticed, right? Let's watch it again. If you notice, a Mars-sized planet smashes into the Earth. Boom. And what happens is all that debris went into space. Look. It went into space, and some of it got locked into orbit around the Earth. And that became the moon. That's what it looked like, essentially. That's incredible, right? And we know that on these rocks, these are carbonaceous chondrites that contain water. There's water locked in the hydrates in the rock. Remember, in that debris around the star was all kinds of materials, water, and all types of even organic materials that form in space. And the Earth collected many of these rocks that contain water in them. And that's how we got our water on the Earth. Those rocks contain water smashed into the Earth. And you have a very warm core, right? And the heavier metals sunk to the center of the planet, right? Notice iron and nickel, right? The heavy metals, they sunk because of their densities. They're way more dense, and hence they sunk. The things with less density floated. They went towards the top, and they became the crust, right? Silicon, right? Things like that. And that's what separated the different layers of the Earth, the densities of materials. Now we have a crust, we have a core, we have a mantle, and we have a cooling planet. And remember, there's water on this planet because we got hit with all these ice rocks. So we have, over time, an ocean form. We have that water precipitates, condenses back down, it falls back down as rain, it becomes an ocean. And in the ocean, you have about 4.2 billion years ago, abiogenesis occur. And this is the fun part, right? This is where we get life itself. Now, in the early Earth, about 4.3 billion years ago, what you have is uranium. Uranium naturally occurs, and it's radioactive. So what happens is this rock can decay over time. You can get geysers that are made of uranium, and they can decay and give off energy in the process. So they can heat the oceans underground. The oceans of the early Earth were bubbling with heat, and that heat in the oceans fueled the reactions required for life. So we get hydrogen, methane, ammonia, right? These basic gases in the Earth's atmosphere. right? Because remember, the gases became the Earth's atmosphere. And some of those gases, when they mix together with some electrical energy from perhaps lightning, what you get are amino acids. You get amino acids you get organic molecules from the reactions occurring in the early Earth's atmosphere. And those organic molecules then become amino acids, which then form chains of which they themselves react with other amino acids. They themselves become peptides, chains of amino acids. Then they themselves become larger polymers or polypeptides. And those polypeptides then form sheets of amyloids. And these amyloid sheets, they get larger and larger, they react together, and they can break off over time, and they themselves can create more amino acids on their own. So we have an autocatalysis happening, right? We have the very early forms of life happening, proto-life. See, that's what life really is, just a chemical process, a very intricate chemical process. And this is the beginning of it. Quite amazing. Now, we also have lipid molecules form in the ocean, and these lipid molecules also interact together, and they form these little bubbles in water. This happens in water all the time. You take lipid molecules, they spontaneously form these lipid bilayers that look like bubbles. And that's where the first protocells began. Those bubbles then encapsulated those organic molecules that can replicate, and you have the first cells. You have the first living beings about 4.1 billion years ago in the oceans of the Earth. And after that, you have just takes off, right? Now you have natural selection. Now you have these beings that are replicating on their own, and natural selection takes over. The survival of the fittest. The ones that can survive in their environments are going to survive. And now we have an explosion of biological evolution take place. You have bacteria. Then you have worm-like animals in the oceans. You have these fish-like animals in the oceans, right, with spines and skeletons. And then you have larger fish. And then you have amphibians, right? They develop little legs so that they can walk on land, because over time they were better able to survive if they went onto land, right? A new habitat. And remember, during this time, about a billion years ago, about 500 million years ago, there were no trees yet. This is when trees began. So, remember that bacteria I was talking about? All that bacteria in the first few hundred million years of life began to make all that oxygen. Remember photosynthesis? They began to take in CO2 and sunlight, and they produced oxygen and allowed oxygen to fuel these living beings on land. So then you have trees as well, and trees gave oxygen as well, but they also provided habitat for animals. So now you have amphibious creatures, and then the first reptiles about 250 million years ago. And then from the reptiles, you have a splitting of mammals and the dinosaur-like animals about 250 million years ago. The first land animals. Remember, mammals about 250 million years ago were not like the mammals of today. They were far more reptilian-like. Okay. But over time, they went their own ways and became even further different. Now we have dinosaurs, right? Dinosaurs stem from the first reptiles on land, and they developed to be large because of all the access to the trees and food and oxygen and everything around them on their environment allowed them to be large. And there was a continental drift was occurring, right? So around this time as well, the continents were drifting around the Earth's surface. And for the longest time, Pangea reigned. And there was very little availability for... There was a lot of climatic problems with that. Pangea allowed the middle of the continents to be very dry and very deserted. But after Pangea split, this allowed for dinosaurs to emerge and take advantage of the coastal environments that were a bit more nicer, but more warmer and not too deserted. Now, so we have an explosion of dinosaurs. Dinosaurs were very diverse animals. They reigned for 200 million years on the planet. But then, we all know what happened. 66 million years ago, an asteroid comes tumbling down towards the surface. And bam. Dust and debris from the impact surround the entire planet. Ash and acidic rain just rains down on the dinosaurs. They die. Many of them die almost immediately. But for the ones that survive, it's terror. Because all that dust and gas is in the atmosphere. They can't breathe. It's hard for them to breathe. It's also very cold. It's blocking out the sun. The Earth's temperature dropped about 15 degrees Celsius in just a few years. And this destroyed lots of plants. Now they can't eat their food. So they began to die out over many, many years. And this is terrible for the dinosaurs. Only the birds survive. Only the bird-like animals survive. The ones that can fly and are a bit more mobile and are a bit more scavengers, right? Because they can eat off the dead plants and dead trees and live underground. Those animals survived. So it was the birds, bugs, and the mammals, the small mammals that lived under the rocks in the ground. You see? This is where our ancestors come from, our most common ancestors, mammalian ancestors. And so now the dinosaurs are gone, and the small mammals can go out there and eat whatever they want. They can go out, they can live anywhere without having to worry about every dinosaur trying to come and eat them. Because remember, they were being preyed on by all the dinosaurs that were like, the smaller dinosaurs, like the turkey-like dinosaurs. And now, without them there, they can live and be happy and be free. And they can evolve. And this is the age of the mammals. And what you have are these mammalian-like animals living in trees. They begin to jump and hop from tree to tree. And they begin to eat fruits. Because remember, fruits were very new about 60, 70 million years ago. You didn't really have flowers but before that time. Flowers and grasses. Those are very new things about 70 million years ago. The dinosaurs didn't have that. So the mammals were able to take advantage of the new food source and live in the trees. You see? They lived in the trees and they ate fruits. And they were able to evolve in a very diverse ways. They spread across the earth. There were mammals that lived in trees in North America, South America, in Asia, in Africa, and all the continents around the world. But a particular mammal that had evolved to live in Africa began to, without very little predators, began to evolve into apes. Right? Monkey-like animals evolve into ape-like animals. And those ape-like animals lived in Central Africa, where at the time, about 7 million years ago, they were chilling. Everything was good, right? They were in the trees eating fruits. But something bad happens. The Rift Valley in Africa begins to diverge. and mountains form, blocking rain from reaching the interior of the continent. And it becomes drier where they live. It becomes drier and drier and drier. And they have no choice but to leave the trees. They can't stay in the trees anymore. If they want to eat and survive, they have to leave the trees and walk on foot. So they begin walking more and more on foot, right? Miles at a time, miles, looking for food, looking for water, looking for new habitats, and they begin to evolve into humans. They begin looking at their environment and using tools, stones, fire. They discover fire in their journey through Africa. They discover how to live in new habitats, going across continents again, going into Eurasia, going into other territories. Then they go, wait a minute, why do we keep walking? Let's just farm, right? Let's just seed things, because they notice that seeds are what makes the fruits and makes the foods happen. And so they start farming. They start throwing down seeds. And this is the spark of civilization about 12,000 years ago. The first city about 8,000 years ago, where people in Mesopotamia, for example, they began to live in a city where they had boats and these little canoes. They would, trade food. They would trade goats and things, and they would, chill out in this little city. And then they discover math and religions and things, and then it gets crazy, right? Then you have people fighting, and oh no, that's my land, that's your land. Okay, let's trade money. All right, let's make a financial system here. All right, let's make a wheel. Let's make weapons to fight. Right? Oh, okay. Let's write things down. Let's put something on a piece of paper so that my future generations can learn, not just me. Right? So they develop literature. They develop language, written language, and paper. Right? Or scrolls at this time. Right? Through that couple thousand years ago, it was just scrolls. And then Copernicus comes around and goes, wait a minute, guys, the Earth ain't the freaking center of the universe, right? There's something more out there, right? Let's discover the laws of the planetary movements, right? Copernicus goes, dude, this doesn't make sense. There's got to be a way the universe works. And he was inspired by religion. He was inspired by, how does God's mind work? He went to seek for the way in which God's mind works, but he discovered something vastly different. He discovered that the earth ain't the center. It's the sun. The sun's the center. And that made people go crazy. And that sparked a revolution about, how to discover these things. Right? People began to get more curious about science. And then we have Newton about, 50 years later. And he comes out with his laws of motion, right? And he discovers that how light works, how there are prisms and telescopes, and how planets really move in our solar system. And this sparks the Industrial Revolution because people further begin to learn about physics. They learn about how things move, right? And energy, momentum, all these things that Isaac Newton discovered and wrote down in mathematics, right? Calculus. Those are very important for making these discoveries. And so, about 1790s, we have the first steam engines. We have powder. We have the automobile in the 1900s, right? We have larger boats that can transport more things longer, and we have space age from this, right? We have Einstein's equations now. Now we can go to space. Now we can do all these things because people use their brains. And then we have the moon landing, where we land on the moon, the internet, right? We use technology to build satellites, communication, the Hubble telescope, We learn more about the universe, right? Exponential increase in technology because we keep compounding our knowledge. It keeps compounding. You see? We were no longer tethered to the trees. Now we could leave it, and that changed our species forever. It changed the way we interact and learn. And now we have, all these technologies, social media, AI, and here we are, present day. Here we are, present day. Where we have carried with us throughout these 13 billion years all that cosmic and biological baggage of our past. That's something to be grateful for. Wow, we're here. We're freaking here. We're alive. We're able to do these incredible things because our ancestors had the courage to go, let's learn. Let's work together. Let's not just follow whatever that guy said in his book or what this religion says. Let's learn about the real world and how it really works. And if the answer makes us frustrated, it's okay. I'd rather be uncomfortable in the truth than comfortable in a fairy tale. And that's what changed us, right? When we started becoming courageous enough to learn and expand our knowledge. And not afraid to exchange ideas. And that's what makes us human. Nothing else makes us human except for that. We're very much like the other animals. We shit, we eat, we piss, just like everything else. But what makes us different is that we use our knowledge to enhance ourselves and our species. Now, any questions? What kinds of questions do you guys have? Anything you want me to talk about? Explain why we still have apes. Okay, let me go ahead and talk about why apes, why we don't have apes right now. Ape evolution. Okay, so if you notice all right, fine, I'll reverse it. Jeez. Okay, now if you notice, you see a tree here, right? You see this tree of whatever. Now, this is about 9 or 10 million years ago. Remember, I was talking to you about the fact that about 10 million years ago, there were apes in Africa. These apes were our ancestors. We come from those apes. But how? Well, in today's world, we see all these apes. Okay, we see orangutans, gorillas, humans, bonobos, chimpanzees, bonobos. These are all modern apes. However, if you notice, they all share a common stump. So you can see the ape back here about 10 million years ago, it split off into different species. So this ape population branched off, and some went to this way, some became orangutans, some split off and went this way. Okay, then they split off again. That population of apes split off again. They became gorillas, and this went on to move on. And then they split off again. Those apes who were very closely related to gorillas and chimps split off to become other apes and humans, right? And then those apes went off to split off and became those apes. So that's how evolution happens. It's a tree. We all share common ancestry. Every animal, every tree on the earth today share common ancestors. if you go far back enough, about 4 billion years ago. But apes, great apes specifically, share a common ancestor about 10 million years ago, and that's what we see in the fossil record, in our DNA. Our DNA is full of evidence of our evolutionary past. There are viruses that have infected our DNA in a way that leaves marks, and we can see that we share very common marks. These are endogenous retroviruses. We share very common DNA to chimps. In fact, we share about 99% of our DNA with chimps. So you can see the closer they are to us on the tree, the more similar to us they are. That's how evolution works. So everything's related to you. Every person is related to you in some way biologically. Every tree is related to you. Every blade of grass is genetically related to you. If you go far back enough, we share a common ancestor. We share a common stump on the tree. And that's how evolution works, because it's always happening. Very good. Any other questions? I don't like to mirror the video because I don't like the way okay. You mentioned the rift that split, causing the leaf trees. Could you talk a little more about it? Yeah, if you notice in Africa, there's a rift valley. And what happened was, as the rift valley diverged, it lifted up a mountain. Because that's how mountains form, right? They form because of tectonic plates diverging or converging together. And a mountain forms, and a lot of that condensation, a lot of that water in the atmosphere was blocked from entering into Africa. So it became dry, right? It became very dry, and it forced the apes to leave the trees, because trees became more sparse, right? So the reason why our apes' arms got longer and longer is because trees became a bit more sparse over time, and they had to reach out larger for fruits and things. But after a while, the trees became so far apart that they had to leave the trees entirely and walk on foot. And that's when we became bipedal, right? Not like in a day, but obviously over many, many generations, the apes that could walk further, they survived. And they became our ancestors. Very amazing. Very amazing. Why don't we have different variations of humans? We do, in a way. Every one of us are different genetically. But we're so very similar that we were the same species. We're not that different, right? But there's very small variations, because we have lived together, like it or not, we have lived together as a species for a long time. And we've always been communal, and hence we have not varied that much through our time like other species. Neanderthals were a different species of humans that existed in Europe about 500,000 years ago until about 50,000 years ago. They died out. They were the last remaining humans with us. In fact, there were many different variations of humans that lived with us in our past. It's just that today we are the ones that survived. Neanderthals, Denisovans, they all died out except for us. Now, we don't know why they died out. It could be disease. It could be that we, dominated over them. It could be war. We don't know really why they died out, but they did. And we have the fossils. We have their fossils. We can see all these different human species. It's quite incredible, right? That our ancestors learned to live in Europe in the colder climates where they had access to mammoths. They could eat more food. They were very, very smart, very, very tough. Yes, some of the Neanderthals, commingled with us, right? They essentially made babies with us. And so we kind of absorbed some of their genetic code, right? So that'll also do with the fact that they left, because we just absorbed them. And, yeah, there could be all the above. All the above could be true. Any other questions? What else did you guys want to learn about? I don't want to talk about philosophy. It's boring. Do you know anything about the topological state of matter? No. Tell me how you can't evolve out of a clade. What? Oh, tell them how you can't? Parallel universes. What about them? Ekperiodic universe. So, parallel universes could be possible in several ways, but one way it's possible is if that there's a beyond the Big Bang, there's another universe that's in reverse to ours. It's the reverse of ours. It could also be the case that we live in a larger landscape of universes in an inflaton field. That in this inflaton field, there is a pocket of space-time like ours that happen to inflate and stop inflating. But the other regions of the inflaton field are still expanding very rapidly, and they're still creating more space and time. And so that could be the case as well. There could be other bubble universes. There could be pocket universes around us. And so it could be the case that we live in a multiverse where there's other bubble universes interfering with ours. And that could be why we are seeing dark energy decrease. In a sense, its intensity is decreasing right now. We're now discovering that the universe seems to be actually starting to collapse in the future. Not right now. Right now it's still expanding. But in the future, it might collapse again. And this could be because of other bubble universes interfering with ours, disturbing dark energy. And it's possible. We don't know that. We don't know yet. There could be many answers to that question. How did the first self-replicating molecules turn to life? Well, that's what life is. Life is merely the replication of stuff. That's it. That's all life means. The only reason why you're alive is because you're replicating. There are cells inside of your body that are replicating. There is a metabolistic process that's occurring in your body that's allowing you to breathe and think and do these things. That's all the reasons why you're alive. There's nothing more to it. You are a symphony of biochemical reactions energizing your life. That's it. Right? Think of an instrument. Think of the notes a guitar makes. Every string is a collection of notes. Right? Now imagine 2 guitars, 3 guitars, right? Now they're making songs. Imagine a microphone. Imagine a cello, whatever, all these different instruments. Imagine them all working together and making a song. Well, that's what your body is like. Your song is like a song of all those things, those little instruments collectively making something happen, and that's what life is. Think about it. It's quite amazing. Consciousness is considered to be beyond particles and chemicals. But why? Why must it be something beyond particles and chemicals? I mean, that's what people thought about life. People thought 1,000 years ago that life was just a soul. There was something beyond particles. But now we know that life is just a chemicals. Why can't the same be said for consciousness? Why must there be some specialness to it? I think that's just what humans do when we don't want to come to grips with the fact that we're just molecules. Molecules don't think or feel, right? Just like a molecule isn't alive. DNA is not alive. DNA is just a molecule. That's it. On its own, it's just a molecule. But what makes it come alive is when it interacts with other molecules and replicates. That's why you're alive. So again, you're forgetting the emergence of life. In the case of consciousness, the emergence of consciousness from particles. How do we get DNA? Well, DNA is an evolved form of RNA. And RNA is just a collection of nucleotides that polymerize into a nucleic acid. Where do nucleotides come from? Well, they come from smaller molecules, right? They come from amino acids. They come from nucleobases that are formed in a very similar way to amino acids. So the ingredients of life are not very extravagant or special. They form in very similar ways. Now, it's complicated how life happens. Very complicated. And that's why we still don't know exactly the full puzzle, right? There's still some missing pieces to the puzzle. But we have enough pieces to the puzzle that we know that, yes, RNA forms from nucleotides that polymerize near clay phosphates. We know that lipid bilators form through lipid molecules in water. We know that amino acids form from gases in the atmosphere and material in the ocean. We know the mechanisms for life and how it began. We just don't know every single piece to the puzzle. But that's not... But we're getting there. We're getting there. Progress is being made. Let's look at some James Webb images. Ooh. Here we have nebulae. We have amazing stellar nurseries. These are big giant clouds of gas and dust in the universe. Some of these are light years wide, thousands of light years wide. And this is where stars are born. Here's some galaxies. Here, I have a book to better see it. Oops. Here's a book to better see. These are Hubble images, though. These aren't James Webb images. Oops. How do I do this? There's a beautiful galaxy here. Let's see. Here's a cluster of galaxies. There are moon galaxies too. We actually have a satellite galaxy that orbits our galaxy. It's funny how the universe works. Here's a galaxy edge on. Nebulae. Here's the famous Horse Nebula. It looks like a horse head, but it's a big cloud of dust and gas that makes stars happen. Remember? Here's the famous Orion Nebula. I mean, beautiful image. Now, these colors are not the colors that you would see if you were to look at it with your naked eye. But, I mean, they're obviously colorized to a degree, but they are made of materials alcohols and all kinds of weird organic material that correspond to different colors. These are real images. These are real structures in the universe. They're just colorized a little bit to make us see the different stuff better. Here's a more close-up photo of the Horse Nebula. No, you shouldn't hate when NASA does that. If they didn't do it, you would just see a black and white photo. Unfortunately, we have to color these images for us to see them, because we couldn't see them with our naked eye. We don't have the ability to see the great pillars of creation. These are real structures in the universe. These are real things. They're quite amazing, and we can see them for the first time. We're able to see them in our universe. A lot of these images contain little dots, and that's stars. Those are baby stars that are going on to become adult stars. Just like we go through different phases of life, so do stars. Here is a nebula, a planetary nebula. Now, the reason why it looks so circular, right? It looks like an eye. The reason why is because in the middle you see a little star. And this star has died. It's a dead star. However, the gases and dust are being shed from the star itself. That's why it looks so symmetrical and spherical, because all the gases are being spewed away from the star in a very symmetrical way. The star is essentially dying, and it's shedding off these layers into space. And that's what our star that's how our star is going to die in about 5 billion years. Our star is going to swell up our sun is going to swell up into a red giant as our sun fuses hydrogen and helium, but not carbon. It doesn't have enough mass and gravity to really fuse carbon together, to do carbon fusion. It can do it on a very small scale, but there's only so much it can do. So that's why once the star runs out of hydrogen and helium, our sun is going to inflate as it succumbs to gravity and the pressure it creates in cell. The equilibrium will be disrupted. It swells up, but then gravity takes over again as it runs out of fuel entirely. All right, so here, energy will ramp up. It'll cause it to turn into a red giant, and then it will gravitationally collapse again as it runs out of fuel entirely and into a white dwarf. This will be a very dense star, about the size of a city. It'll be the size of maybe a state, for example. But it'll be very dense. It'll be a white star or a white dwarf, and it will shed off all those layers that it contained inside. And there's all kinds of stuff in our sun. There's all kinds of materials in our sun, iron and things and all kinds of elements. And it will turn to like something like this. Quite incredible. Our star will not explode. It's not massive enough to explode. But there are some stars, many stars out there that have enough mass to explode entirely. And some of those stars turn into black holes. Right? Some of those stars that have enough mass, that have 10 to 20, 30 times as much mass as our sun. Some of those have enough mass to turn into black holes. Those are called stellar black holes. But our sun doesn't have enough mass to do that. Our sun is an average star. Now, most stars in our galaxy are smaller than ours. Most stars are red dwarfs, and most stars in our galaxy are binary. So in other words, there are two stars that orbit each other. Our sun is relatively unique in our galaxy, relatively speaking. I mean, most stars are not our size and don't have as much temperature as ours. So in a way, we are a bit unique in our galaxy. Why do suns burn if there's no oxygen in space? Well, they're not burning. See, it's not a burn like you think, like a fire. A fire, you need material, you need oxygen to burn that. But a star doesn't burn like that. There's no combustion happening. It's a different kind of burn. It's a nuclear burn, in which atoms themselves are colliding together, fusing, and generating energy from that process. Atoms contain energy. Remember the E equals mc squared? That equation describes this very thing. There is energy contained within atoms, if they're hot enough. And in the star's core, these atoms are very hot, and they contain lots of energy, and when they collide together, they fuse together, some of that energy kind of sheds off, and it is light. Some of it's gamma rays or beta, but some of it is visible light, infrared, invisible. And that is incredible. So the reason why you're alive is because that star's atoms are fusing together, going through space, traveling all that space, hitting the oceans, hitting the earth, generating energy to feed life, feed plants that then feed you. So in a way, we are all solar powered. Black holes as we know it, and like Interstellar, are those images edited? The interstellar black holes are very accurate in terms of this image is very accurate. This is a very accurate image. Come on. This is how a black hole really would look like if you were to see it. Very, very accurate. Now, the reason why it looks like this, looks very weird, right? Is because this is the black hole, actually. This right here, the blackness is the black hole. The stuff on the outside is light that is spinning very fast around the black hole. It's spinning so fast. And the reason why it looks so warped is because the black hole itself has so much gravity that it's warping the space and time around it, such that if you look at the black hole straight on, you see this disk and this center disk, because the light from the back of the black hole is going up the black hole and it's going sideways. So you can see the light going up from the back, right? Imagine the light's coming back. It's being intercepting the black hole's gravity well. It's going up, and that's the warped light from the back of the black hole that you see. And this isn't really how it would be like, right? But this is just an illusion based on the fact that the space-time is being warped by the black hole itself. So that's incredible. Can you address people saying attempts to measure and understand the universe through science is seen as religion? Okay. People are saying that because they want to devalue science such that it makes their religion seem more, what's the word? Reputable, right? They want to make it look like the religion is is as reputable as science, right? They try to knock down science to make them look better. The problem is that religion is a method. Religion is simply a belief system. It's simply a doctrine. It just simply tells you this is true. Believe it or else, right? The difference is that science doesn't just say things. People forget about that. Science doesn't just spit out answers to us, right? Science is a method. It's a way of thinking. It's a way of navigating the universe in a way that would yield you results that they themselves are testable, that they themselves can be repeated, that they themselves aim to reduce bias, right? Because look, with religion, lots of bias gets in the way, right? Because you want to believe that God is good because you want God to be good. But under science, we don't just, if you want the sky to be red, well, I'm sorry, but, you know, the world, or if you want dark matter to be false, well, I'm sorry, but we can perform experiments that demonstrate you are incorrect. And that's the beauty of science. It aims to get rid of those biases in our experiments, and we describe the method in our papers. When we do science, we don't just do it, we also write it down and make sure that the methodology is accurate and solid. And we write down our conclusions, we write down how we did it, and we make it so that anybody else can replicate what I did and fact check me. And if I'm wrong, I don't go, wah, no, trust me, I have faith in this. If you're wrong in science, you go, thank you, I now learned something new. So we're not scared of being wrong in science. We like being wrong sometimes in science because it makes us learn more. So those are the key differences between science and religion. Can you explain the Higgs field? The Higgs field is simply a quantum field not a quantum field, I'm sorry. It's a field within particle physics that describes why certain particles obtain their mass. It's a particular field in which particles move through it and they gain mass. It exists all around us. It exists everywhere in space and time. It's just that the energies required to observe it are so large that you need a large hadron collider to cause two interactions of two protons that would jiggle out a Higgs boson, which is a particle from that field. So that's what they did in 2012, right? What they did was they collided those protons and it jiggled apart a particle from the Higgs field itself. Now, it's not like it just floated away. It's like, yeah, it was a mathematical thing entirely. And it's not like they took selfies with the Higgs boson, but they observed energy disruption that was predicted by Higgs, the guy who discovered the Higgs field. So, yeah, it's quite incredible what they discovered. And kind of in a way that was essentially supposed to be a nail in the coffin for particle physics, such that we have all the particles we need and we have the Higgs field, which derives their masses. But it turned out to be not quite the case. There's still more to learn about particles, and quantum mechanics is that endeavor. What are some of the other fields? Well, there's a field to every particle. There's a field to everything. Is there an explanation for the double slit experiment? All right, let me go ahead and explain the double slit. The double slit experiment aimed to let's see. shoot. How do I wasn't planning on this, but let's see. Okay. So, shit. You guys can't see it, can you? Is that okay? Can you guys see that? Anyway, I'll just keep going. All right. So you have these little electrons here. All right. You have these little blocks. You have slits in them. So you have two slits, and you have little individual photons or electrons, whatever kind of particle you want to choose. You shoot them through straight. They go straight through as you shoot them through. And this is what you kind of expect, right? You kind of expect two lines at the back, right, where the photons strike the backboard, right? So you expect two slits and two rows of patterns. The problem is that when scientists put little photon detectors or particle detectors here and here, they discovered that they did the experiment again. They shot individual particles through the thing, and they discovered, instead of two straight lines, they discovered a pattern. They discovered this. Right? They discovered a pattern of light at the back wall. And they were confused. Like, why is this the case? We shot individual photons one by one, but we expected two rows. Now we have several different rows. It seems as if we've gotten an interference pattern, right? This is like what you get when you see waves in a pond, or you see the waves interfere with each other. That's kind of like how this happened. So it must be the case. Now, hold on. When they took away the detectors from the experiment, it went back to this. They took away the detectors, and it went back to this. The individual rows. The detectors changed the outcome of the experiment. So it turns out what the experiment found is that light can act as a wave, as particles, or a wave. Or a wave. Because that's what that wave pattern was. It was evidence that that light was a wave. The light would go in, and the photons would act as a wave. So why? How do photons act like waves? Well, the answer could be, we don't know the answer. We still don't know the answer. But the answer could be the case that when you are not measuring the system, the photons are in a superposition. Now, this is quantum mechanics, right? A superposition where the photon is existing in all different states. And when you put so there's a wave function to that photon, but when you put the detector there, it collapses the wave function into a single row, right? So this is what they kind of guessed, that there's a wave function to the photons, and they exist in superposition when you're not measuring them, but when you do measure them, the wave function collapses, and it turns into a single photon that is measurable. Okay. And no, it's not because they're looking at them or they're conscious of the photons, right? This happens whether or not you're conscious of it, right? This does not require consciousness. There is an interaction that occurs between the photon detector and the photon. And it could be that there's an entanglement happening, right? There's an entanglement happening, and it could be the case that that's why the wave function collapsed. Or if you're an Everettian and you don't believe in wave function collapse, what happened is something even crazier, that the photon that you were observing is the photon that exists in your world, and there's another world where you exist seeing the photon in a different space. So there's many different worlds indexed to your superposition, to the superposition of states of photons and you. So the entire system exists in different states in different worlds, and you're just in the world where you saw the photon hit the back screen in that particular way. Yeah, it's deep. Very deep. But again, we don't know, this is all hypothetical. We don't know the answer. We don't know the full answer. Okay, there's so much. But what the experiment did do is demonstrate that photons do act as waves and can act as particles. What is your favorite accuracy in Interstellar? Interstellar. Let's see. I think the Tesseract was freaking awesome, you know? And the Tesseract is crazier than it looks. Is even more, when you understand the science behind it, it's even more amazing. The cornfield? No. So the reason why I think the watch scene, the one where the watch scene is my favorite part. So let me actually, I have the movie here. Let me bring it up. I have the entire movie on my computer. I love that scene. I love the man's planet. That was pretty cool.
Goodbye, Tars. Goodbye, Dr. Grant. See you on the other side, Coop. See you there, Slick.
So this is so the Tesseract is connected to Murph's bedroom. Right? That's why it's like this. The Tesseract is actually connected to Murph's bedroom. It's docked to it. So one side so where Cooper is in the Tesseract is just one face of the Tesseract, and the other face is Murph's bedroom. That's what the aliens did, right? The future humans, whatever, the 5-dimensional beings. They set up the Tesseract so that they were both connected. So Murph was on one face of it, and the other face was Cooper. Now,
Just like I found this moment.
the reason why it looks so weird like that, why there's light, all that stuff, all those light, those are books. Those are books. Okay? All those lines are the books of the damn room. Those are world lines. So in relativity, you can essentially trace back every single particle that ever existed. You trace it back for its entire existence through time, and you find it has a world line. So it's very hard to imagine, but imagine the universe as a block, and there's 3 dimensions of space, but 1 of time. Okay? Every particle exists in 4 dimensions. So it's not just, when I wave my hand, it's not just waving my hand and there's nothing happening. I'm waving my hand and there are other hands behind my hand. There's a line, there's an entire row, an infinite row of hands behind mine that correspond to the different times. Does that make sense? Every instant in time is another hand, right? So that's what this is like. Right? Every particle of the book is in a line through space and time, and that's what this was. This was. Now, come on.
People couldn't build this.
All right, here it is. All right, perfect. Okay, so what Cooper is doing right now is he's manipulating the world lines of the watch. That's crazy. He's changing the world lines of the watch itself. Every particle in the watch, he's changing by moving its world line through space and time, because he has access to that through the Tesseract. That's mind-blowing, right? When you actually understand what this means, it's crazy. He's actually changing the world line of every particle. So he's changing the time. Now, the reason why it's stuck like that forever is because in the Tesseract, he was in a loop of time. He was in something called a time-like... I forgot what it's called. Shit. A time-like curve or something. Anyway, he was in a loop of time. So everything he did in the Tesseract was in a loop that happened forever. There was no end to it. That's why it is always like that, because he was in a loop of time. And this, it's hypothetical. It's not like real thing. It's not like reality. But I'm saying it's a hypothetical thing about space and time. That there are, you can create a little loop within the grander timeline, and you can have infinite things happening in that loop. So yeah, I think that was the coolest part. But there's so many cool parts, right? So many cool parts. How would a 4D being experience time and causality? They wouldn't see time like we do, right? Because we only experience time like it moves because we don't see the full picture. We're trapped in 3 dimensions, or in 4 dimensions, right? But if you were in a higher dimension, you could see all of time at once. So you wouldn't see the passage of time. You would see all time existing at one time. But again, this is just like we're going to some fringe place now. We're not going. We're in the Matrix. That was a real cornfield. Yeah, I know, but big deal. Like, wow, it's a real cornfield. Interstellar was written by Kip Thorne, who is a scientist, who is essentially one of the greatest scientists ever. People don't understand that. People are like, oh, whoever wrote that is great. Yeah, he's a scientist. The science behind Interstellar was the first thing that was written in the 90s. If you right after Carl Sagan's movie Contact came out and was a big hit, Kip Thorne was like, oh shit, let me make my own damn movie with science. And in the 90s, he thought of this idea. I mean, it was vastly different, but yeah, in the 90s, he began the story. And it developed over time. He gave it to Hollywood. He gave it to other places. They get off to other people. But eventually, Chris Nolan got to it. And he kept a lot of the science, but he changed a few things. And here we are. We got Interstellar. Yeah. Yes, Interstellar is one of the most accurate movies. Yeah. By far. It's hard to find very accurate movies. Another one is probably The Martian with Matt Damon, is it? That was a good one. That was pretty accurate. Star Wars? Hell no. I don't like Star Wars. How do we know that redshifted light is caused by space expanding? Well, we can also see distance. galaxies don't, there's parallax to galaxies. We can observe how far away they are from us, and we see that galaxies are moving away from us in a very consistent manner. But yeah, I forgot what I was going to say. Why was the ground in the sky in the end? Oh, yeah. So, so, yeah, this scene, right? Why was there this thing here, right? What is this? That's so weird, right? Like, what is that? Well, this is something called it's in the movie it's called Cooper Station, but it's something called I forgot, space cylinder. O'Neill cylinder. Okay, yeah, it's called an O'Neill cylinder, made by a guy named O'Neill, who devised this kind of thing where it's like a big giant tube in space, and it spins. And the spinning creates kind of a gravity field, kind of, right? Because of the way the physics happens. I'm not a physicist, but it turns out when you have something spinning in space, you get momentum and you get an illusion of gravity, right? So that's what they were kind of trying to do here. It would spin maybe once every minute or something, but it's a big thing. And that's where they were. That's the station that they made for the humans to leave the Earth. Because actually, that's what Interstellar is about. Interstellar is about the Earth is getting fucked up. They didn't know how to. They had these big ass stations that they made. They wanted to ship off the Earth, but there's too much gravity to do that. So they had to get the gravity equations to slow down, to change the gravity for the Earth so that they can lift them off into space. And that's what they did. I know it's stupid. The story is stupid, but it's cool that we have, these awesome space stuff. Do you like Arrival? Yeah, I like it. It wasn't really sciencey. It was more like a, language thing. But I think it was a cool, cool idea. Definitely different. Not realistic, though. Not very accurate in my eyes. How do dark matter and dark energy shape the universe? What's their nature? Well, dark matter is just like matter, like our matter. It's just that it doesn't interact with light. So you can't see it visibly. And that is actually there's actually more dark matter than there is regular matter like us. So dark matter is actually dark matter is going through your body right now. It doesn't really interact with you. If you were to you couldn't hold dark matter in your hand. It would just go right through your hand. That's crazy. That's crazy. But it has a gravitational effect on us, right? So it gravitationally can be observed. We can see the dark matter clumps causing gravitational lensing, causing gravity to light to be distorted. When we look through telescopes, so we can see dark matter indirectly, and we also can see it with math. We can observe the galaxy rotation, and we find that it's spinning faster than we thought it would. When we account for all the mass in our galaxy, all the visible mass, it's not enough to account for the rotational speed of the galaxy. So when we add dark matter into there, and we add this little halo of dark matter around the galaxy, it makes all the sense in the world. Now it makes perfect sense as to why the galaxy is rotating this way. So dark matter is essential. We just don't know the nature of it. It could be dark matter is just a type of particle like a neutron, just different dimensions or different properties. It could be, some have hypothesized primordial black holes. These are microscopic black holes, so you can't see them, right? They sink in light, but they're all around us. You know, people don't realize that just because you have a black hole doesn't mean you're going to die. There could be black holes right now all around us, little microscopic ones that have very little gravity. So those could be things that were produced in the early universe that then gave rise to the structures of the galaxies. But there are many, many other ideas, and I don't know all the different theories, but there are theories about how dark matter happened, and they're all interesting. They're all quite interesting. This stuff is mind blowing, and if just think about how the average person doesn't understand this, and how amazing it is to understand all this. It just makes you more appreciative of the world around you. And I know it does that to me. To me, I am so appreciative of living in this world because I understand it better. And that's all I want to convey. That's all I want to convey to people. That's why I do this, you know. That's why I talk about the God thing. Like, I don't give a shit about God. I don't give a shit if God exists or not. I really don't care. But I debate because it helps people think about the world around them. And the same with every topic. And that's all I want to convey to people. That the world is better when you understand it more. Okay. How do you know that about dark matter going through your hand? Because we know its properties. It doesn't interact with us. This isn't Saratoga. This isn't. This is actually tap water, but I just have a Saratoga bottle. So by inferring through its gravitational properties, we can infer that dark matter doesn't interact with us. In the sense that regular matter does. It has to be a halo. It has to go through. It has to be a halo for it to make sense. But there are some models where dark matter can interact with us, right? Not all. There's different models. There's different ideas about it. So with redshifting, we see galaxies moving away from us in all directions. Yes, we see galaxies moving away from us in every direction. Now, there are some exceptions because some galaxies are actually moving closer to us because they're closer. The further away you are, the faster you are moving away from us. So think of the universe like a rubber band. You're stretching it, and the parts of the band further away from the center are seemingly moving faster away from the center than things closer to the center. Does that make sense? It's because the entire universe and all of space and time itself is stretching away, right? So it's very unintuitive in some ways. And there is no center. There is no objective center to the universe, right? You can say that we're the center, but every single point in the universe could be technically called the center, right? So again, there is no objective center to the universe because it's all being stretched equally, uniformly being stretched, like a rubber band, right? Like that rubber band I was talking about. The Big Bang is not mathematically impossible. Do you think there's more of thousands of universes out there? There could be thousands of millions of universes out there, like ours. Let me move this now. Okay. Hope you guys enjoyed that, you know. It's a shame that people don't care anymore about learning. It just makes me so disappointed to see people devalue learning and science and education. I don't know what's gonna happen in the future. I don't know if we're gonna make it. What if you were to be convinced of God? I could care less if a God exists, right? God is just a word to me. God is just a word, right? It's like saying, what if Smugglemuffin existed? Well, I don't care about Smugglemuffin, right? It's just a word. What do you mean by Smugglemuffin? It doesn't interest me to talk about God. It's just a word. What it does interest me is learning about the real world, the real stuff that's out there. What can we see? What can we poke? What can we observe? That's what makes me excited. Because those are real things. But to sit there and go, you know, to tickle your brain, to tickle yourself, your own brain, and go, is there a God? Oh, is he powerful? Is he smart? That's, to me, largely a waste of time. Because you're just not really learning anything. You're just talking to yourself and believing in things on your own terms. You're not really learning about the real world. And, you know, as we could see in the comments, people are very keen on being resistant towards science, being contrarian, right? Oh, you're just scared. You're scared of there being a God. You don't want to believe. You just want to be contrarian. You don't want to listen. You don't want to hear others out. You don't want to pay attention. You don't want to listen. You don't want to learn. You just want to say, no, I'm right. You're wrong. Right? That's all you guys want to do. And I understand. It's very human. But it's not a good path. You're just going down the wrong path. You know, part of science is understanding that you could be wrong. That's important. It's important to come to grips with the fact that you could be wrong, and to just dismiss anything that counters your ideas, and just go, no, I must be correct. I can't be wrong. That is a recipe for disaster. It is not. It's very arrogant to do that. It's very arrogant. Whereas science fosters a very good sense of humility. If I look, when you have a very fervent conviction in God, it stops you from thinking about other things that are possible out there, right? Now you're confined, you're imprisoned in this paradigm where God must exist and it can't be wrong. That's the problem with religion. You think you can't be wrong, and you fight so strongly to defend yourself with faith, with emptiness, because you have nothing else to fight with except for your faith. The only thing that's unfalsifiable is your protection. It's your shield, right? Because nobody can disprove you. In your mind, you convince yourself that nobody can disprove me because I can talk to God and you can't tell me otherwise. And you use that kind of belief system to protect yourself from criticism. That's precisely the problem with religion. You get stuck in this paradigm where you believe that you can't be wrong and that nobody else can criticize you. And if they do, there's something wrong with them. They're out to get you. They're out to hate you. You're being persecuted. That is the problem. It leads to extremes in your views and in the way you think. And that is a very shaky foundation. Whereas, I call it a top-down foundation, where you start at God exists, nothing can prove me wrong, and then you work your way down to explain the rest of the world around you, that trying to fit it in and squeeze it in with the view of God. But whereas my view is the utter opposite. It's bottom up. It's you start from the base knowledge. What is the most likely thing to be true? You start from there and then you build. Whereas starting from God must exist is a very, very bad path to truth. If you notice, a lot of religious are religious precisely because they have a so-called experience with Jesus or Muhammad or their select religious idols. Why do they hinge upon these things so much? Well, they do it because that's the one thing that's unfalsifiable, the one thing that nobody can touch, that nobody can say they're wrong about, and them accept it. If you believe that you talked to Jesus last night in your dream, well, I can't say you didn't. I can't show you that you didn't do that. And so you continue in your belief, and you get further indoctrinated. You succumb to further confirmation bias. Every time you dream of something, you go, oh, there is Jesus again, and then you just stay in that belief, and nobody can tell you're wrong, and you kind of isolate yourself from the rest of the world, and you become radicalized. It's a very dangerous path, and science has no room for that kind of thinking. That's the beauty of it, that there is no sacred truth in science. It doesn't exist. Anything we get in science can be refuted. It can be proven wrong. That's the beauty of science, that we're open to being wrong, and we don't allow ourselves to get stuck in those paths where what we believe is unfalsifiable and unable to be demonstrated to be wrong. That's the beauty of science, and that's why it leads to far more fruitful results. I mean, look at the modern infrastructure of the world. Buildings, roads, cars, trains, internets, all these things were designed because of science and not because of religion. And how could you look at the world today and not recognize the power of science? and instead replace it with something like religion as a foundation. Religious often purport to have powerful prophecies. Oh, this person in this book prophesied this event in the book. That's not prophecy. That's foreshadowing. But if you want prophecy, how about science? With science, you can prophesize the very movement of the moon a million years from now. We can predict the exact second and day that a lunar eclipse would happen in a million years from now. We can do it with science. You can't do that with religion, right? There are far more predictions that we can make that are far more powerful than the ones we make in religion. And when we compare these two things, it is so clear and obvious that science is far more productive and fruitful. On every front, it's the case that science supersedes religion. Well, don't get me wrong, religion produces great poetry, good music comes from religion. But other than that, I can't think of any real world fruits of religion that make the world a better place. And such that no other endeavor can do that. I don't believe that religion has monopolized morality or purpose, right? That's another reason why people believe in God. It gives them a purpose or a moral system. But even not only can an atheist do that, but even through science, we can derive a sense of purpose. I mean, learning about the world, as we've discovered today, learning gives me purpose. It makes me happy and appreciative to be alive, and it gives me a great sense of humility. Religion can't say the same. Religion might teach you things, but it just says they're true. You don't know how they're true. You don't know why they're true. There's no explanation given except for, you trust me. God did it. Just believe us. And that leaves lots to be wanted and desired. Far more answers and far more answers to questions can be produced through science that religion cannot ever do. And just like I'm saying, learning about biology, learning about the fact that we share genetic code with other people and that we are closely related to the stars, that we are made of star stuff. Learning these things are very deep, and making those connections that you can make through science. The fact that we're related to trees in a very deep way. That we're related to every living organism on this planet, and we share this ecosystem because of natural selection. And there's a history. We share a genetic history together. We share evolutionary history. We share cosmic history. All these connections we're making through science are far more powerful, far more incredible to understand and come to grips with than, trust me, God made people, right? Where do animals come from under Christianity or Islam? God made them on the third day. I mean, that leaves far more to be desired. It leaves, and versus, understanding the fact that there's a whole planetary, protoplanetary disk that formed, accreted through angular momentum and nuclear fusion, stellar fusion, and we have planets formations and abiogenesis, and all these things are far more incredible, far more powerful and deep than trust me, bro, God did this on the second day. And they are so, or learning about black holes, or learning about the fact that time slows down as you move faster through space. That is so counterintuitive, but it's amazing because it's true, and because we can demonstrate it, and because it is not just something we're told; it's something that we can demonstrate, and that makes it far more exciting and thrilling. Mike, do you believe life started in Africa? We don't know where it started, but humans began in Africa, yes. But life itself could have begun in multiple places. But likely in the oceans, likely in the deep oceans where there were hydrothermal vents nearby with lots of chemical mixing with uranium geysers providing energy, and the catalyst for those reactions. I mean, even learning about life is just amazing, right? Learning about abiogenesis. And look at what the religious want to do. The religious want to dismiss it entirely. Oh, it can't be true. This guy, this philosopher said it can't be true. So I'm not going to believe in abiogenesis. I'm not going to accept it. I'm not even going to look into it. But look at what you're missing out on. You're missing out on so much intricacy and astonishment that we are just these molecules that happen to coalesce in certain chemical ways that are intricate but able to be understood. And there's an evolution to it, and there's a story to it. There's a sequence of events that are far more complicated and amazing and thrilling to comprehend versus, here, buddy, here's the Bible. God made us in 3 days. Science can reveal a whole heck of a lot more than religion can. So on my point is that on every single front we can think of, almost every single front, science is just a far better method to the answers and to truth and to understanding of the world. So the Tesseract could exist anywhere. The only reason why the black hole was necessary is because Cooper had to go into the black hole to discover the quantum equations, right? The quantum information to give to Murph. But the Tesseract did not have to be in the black hole. It could have existed anywhere. It could have existed anywhere in the universe. And furthermore, I mean, look at how religion prohibits you from accepting other people in modern society. Look at all the resistance against the LGBT community. A lot of it has to do with religion. Oh, God doesn't want this. It's literally blocking you off from an entire category of people. And it fosters an anger, a hatred against these people, a very keen resistance. That would never exist if you took it with a scientific approach. I mean, look at all the hate against trans people and gay people. Why is there so much hatred? It's not just because people are bad. I mean, sure, that's a part of it. It's not just that religious people are bad, and that's not what I'm saying. I'm saying that there's an ignorance to the issue. There's a deliberate ignorance. There's a willful ignorance. that comes with the religious approach to these questions, these issues. A part of the religious mentality is, let's not talk about this because, number one, it's icky, it's different, and God says it's bad. So you block yourself off from understanding them. And if you did, you would realize that they're just people like you and me, and there's nothing wrong with them, and that's how the brain works. Gender comes from the brain, and the way that we think about our sexuality comes from the brain, but you're blocked off from all that, and you're blocked off from all that by taking a religious approach to these issues. That's another problem that people don't quite see. So when you ask me, what do I lose from believing? I lose a heck of a lot. It's just that you can't see it at the moment, right? It's just that from a religious point of view, you don't really see all the things you're missing. And that's the problem. Right? Even asking the question, what do you miss? What do you lose if you believe? That's a very bad question. Because you're implying that I don't want to learn about what you have to talk about. I want to just believe what I want to say. I want to believe what I want to believe. And there's nothing you can say that can change me. That's a problem. That's an inherent problem. And religion is set up and configured in a way that stops you from asking these questions that would help you understand the world better and interact with the people around you better. And this translates to different laws, and that creates toxicity in regions of the world. And think of how much toxicity religion fosters and breeds unknowingly. Right? It's just a reckless wrecking ball tumbling down the mountain, just reckless, destroying everything in its path. Anything it doesn't like, destroyed. Anything that even remotely challenges it, destroyed. And the consequence of that is a chaotic world where nobody gets along, where there is polarization, where there is stark hatred and anger towards one another, resistance. And that's what we have kind of got to in a way. Religion is not very prevalent in politics in the sense that we think it is. It's very hidden. It's very hidden driver in people that makes them think the way they do. It's not very, people aren't very open about it. And 100 years ago or 50, 60 years ago, people took religion differently than they do today. It's changed. It's evolved in a way. If you notice, the wording people use to describe their faith has changed in the past 50, 60 years. It's because the progression of society has done this. It's socially influenced them to change their rhetoric to better fit in. So there is pressure on religious folks, and yet it still is a powerful force in people because they take it seriously, secretly. And it controls much of right-wing politics. It contributes to a lot of this polarization going on. And so look, there's a reason why we should be talking about science more. And we should be talking about religion more. And we should be talking about these things more. If we don't, we just let it sit, bubble up, and just get bigger and bigger. But there has to be a challenge. There has to be challenges to these things. We have to challenge other views. And that's what I don't see from the left a lot, right? The left is sometimes too scared to talk about it. Oh, I don't want to offend people. I don't want to offend them. That's a bad approach too, right? So both sides are contributing to this in a way. But again, science would help solve all this. Science, taking a scientific approach would help both sides. But people don't want to take it seriously. People just want to dismiss it. Oh, science is too hard. I don't like it. It's boring. Let me go play TikTok or play this thing online. These are just some concerns I have about the world. The multiverse would not change anything about physics. I mean, it's the multiverse is. I mean, if we discovered evidence of it, that would change some things for sure. But it's not like we'd have to have. There are many quantum mechanical theories that incorporate multiverses. There's no need for an entirely new set of physics. However, yeah, it would shake up a couple things. Even the Big Bang model, even the Lambda model. It could be incorporated with the multiverse. So that's why our standard model of the Big Bang is very, very strong. People don't recognize what the Big Bang model means. It doesn't mean it doesn't encapsulate everything. It encapsulates actually a very small portion of known physics. So people think it's the end all be all. And then, they are under the illusion that if there's any crack in the wall, then the entire thing comes down. No. That's not how theories work in science. We don't take down the entire theory because there's a crack. We fix the crack and keep going and learn more and build upon it more and make it stronger. We never, the same damage that criticism can do to religion is not the same damage that it can do to scientific theories. Right? That's another good thing about science, that it absorbs errors. It loves errors. It grows stronger. It just errors. Let's keep moving. Let's grow with these errors. Religion is so, oh no, you just said that was wrong. Oh no, everything has to fall down. It's very delicate. Science is not delicate. It's not very fragile at all. Where will science be in 30 years? So I suspect that with the advent of AI and quantum computing, science will no longer be done by humans. The forefront of physics will no longer be done by humans thinking. It will be done by computers. Even today, a large part of science is the engine of science. A lot of it is moved by computers. And that's just going to increase in the future. But the sad part is that we're not going to be a very big part of it, at least at the forefront of it. But we will be we will sit back, and the good part about this is that we'll sit back and we'll go, wow, look at what these systems are just learning about the universe. We're going to learn a heck of a lot more in the next 30 years. It's going to be exponential increase in understanding. I think that's going to be exciting to see. You have no original thoughts, simply regurgitating. Well, everything you think is something you've learned. there's no such thing as conjuring up a completely original thought that nothing's ever thought about before. That doesn't exist. That rarely exists. What exists is you learning things. So the idea that I'm doing something wrong by, you know, learning things and demonstrating them, that makes no sense. There's nothing wrong with that. Computers can hallucinate too. Yeah, absolutely. Yeah, AI is not going to be very different from us. They're just going to be a bit more able in many ways. They're going to be have a bit more capacity, right? I'm not saying that AI is going to be flawless. Of course not. But there's a limit. There's obviously a limit to our abilities. There's obviously a limit, and I suspect in the next 10 years we will reach those limits, and systems will supersede us. I never said you were wrong. Well, you were implicitly making you were implicitly saying that there's something wrong about this. Will quantum computers be above human brain? Yes, quantum computers will be far more powerful than human brains. If used correctly, if used in certain ways. I mean, right now they're not. I mean, they're powerful, but they don't have the same utility as a human brain, right? Obviously, they don't have that utility. So that's that's another factor there too. It's not just raw power. There's also the fact that there has to be something we get from these quantum computers. There has to be good fruits, useful results. If we don't have that, we don't really have is it really powerful? How much gigabytes of storage is our brain? Well, we have about 100 billion neurons. And remember, each of those neurons exists within a synapse. Those are connections between neurons. And your brain has about 60 trillion synapses. 60 trillion different wiring, or at least connections. And I would guess it's far bigger than gigabytes. You'd have to use something like a zettabyte. Trillions and trillions of gigabytes. What is consciousness? Well, to me, it seems to be a process in which neurons interact with each other. There is an electrochemical. There are electrochemical machinery happening in your brain. There's billions of things happening constantly in your brain, and that electrochemical emergence creates the brain. I mean, the brain is just the mind is just that. Your thoughts are just the result of the neurons interacting in your brain, and so consciousness seems to be that. You know, that's like asking, what is life? Well, life is a process that emerges from the molecules of life, the DNA and things like that. Life is not DNA. Life isn't the molecule. Life is the process of those molecules, right? So in the same sense, the consciousness is the process of the brain. Now, we don't know the exact mechanism. We just don't know the exact mechanism. It's not as clear to us as life's processes are. But we're learning about the brain processes. And we're discovering a lot about consciousness. And we're going to discover even more in the near future. So lots of adventures will be coming soon. Don't worry. Will the question be answered in a lifetime? Probably. Do each of our synapses necessarily store memory? They don't all necessarily factor into gigabyte storage. Well, yes, your entire brain stores memory, not just the hippocampus. And there's something called engrams, in which you have configurations of neurons and synapses that work in patterns. And every time your brain is stimulated, it fires off those same patterns of neurons, and that's what memory is. Memory is when the same neurons in your brain in configuration are lit up. When you smell something, right? When you smell something, those molecules go into your nose, you have neurons in your nose, your olfactory, which then goes to your brain, and your brain stores them in your neurons and in certain patterns. So every time you smell that thing, it brings up those memories. That's why when you go, when you walk somewhere and you smell something, a whiff of something, and it reminds you of something in your past. It's because those same neurons are being fired off. And that firing itself is what creates the memory and creates the feeling or creates the thought, right? So did I answer your question? Why does time only move forward? Time doesn't move at all. Time doesn't move. That's an illusion. As Einstein said, the passage of time is an illusion. Very deep question, but time doesn't move. Nothing really moves, actually. But you're right. It does seem as if there is a trajectory through time. And this has to do with entropy. Why is it that when I am in space, why is it that on Earth there's a down? On Earth there's a down and an up, right? A down is to the ground, and I throw a ball in the air, we know it's going up, and then it comes down. So there's a clear direction to space on Earth, right? Up and down. But in space, there is no direction. If you throw a ball in space, it doesn't go up or down, it just goes anywhere, everywhere you throw it. There is no direction to space, in space. There's no clear up or down, right? In the same sense, that's how time works. Time has no specific direction. But there are objects, there are events or things in the universe that could give the illusion of direction. And just like gravity can give the direction of time, of space, entropy can be the direction of time. Now, what in the universe can we think of that was had lots of entropy or had very little entropy in the past? The Big Bang. The Big Bang was very low entropy, and now we're in a very high entropy environment. That dynamic gave the direction of time. You see? The Big Bang was like the gravity of the Earth, giving us direction of time. So, why it seems as if there's a direction in time is because of the Big Bang. Now, if you go past the Big Bang, you'll find that entropy reverses. And now there's a possible another twin universe beyond the Big Bang that has reversed time, has, as we would see it, right? Relative to us, it would seem as if that universe is backwards in time. So it's crazy. He said, "Is there a movie about this?" No, this is reality, guys. This is science. That's how incredible science is. So many things to learn about. So many questions that we have answers to. So many great things to think about. Yeah, time is still a mystery. Time is still a mystery. We still don't really know what time is. Now, it's funny that you mentioned quantum entanglement, because quantum entanglement is now an emerging answer for time and space itself. It might not be the case that space and time are fundamental. It might be the case that quantum entanglement is. And the product of quantum entanglement, right? If you notice that in quantum entanglement means that two particles are connected in a way. Quantum entanglement, when it occurs, it might create threads of space and time. And we now are realizing that quantum entanglement happens all around us. And you get all this quantum entanglement happening. What you have is little threads, little fibers of space and time created. So what you get is a fabric. All the quantum entanglement that's happening creates a fabric of space and time. Now, that's how it emerges. That's how perhaps space and time itself emerges. But again, this is super hypothetical, super fringe, not at all consensus, right? This is just a radical idea. But if true, it's quite incredible. Can you explain how life came from non-life? I have a video about that on my YouTube channel. What do you think of Lawrence Krauss? I met him one time. He's a bit weird. Smart, but weird. Have you changed your stance on free will? No, as of this moment, I still am a determinist. So, yeah. What time is it? Oh, it's 11 o'clock. Not too bad. Hope you guys enjoyed. Hope you guys learned something. So you think Schrodinger's cat is just us not being able to predict what's determined? No, that has nothing to do with determinism. Determinism is more of a philosophical point. Schrodinger's cat is the idea that there is a superposition of states without measurement. in other words, if you don't measure something, you're not entangled with that measurement. There's a superposition. You don't know the state of something, right? You don't know if the cat is alive or dead in the box. But once you measure it, once you open the box, there you go. You find out what the answer is. That's kind of an analogy to how quantum mechanics happens. Now, the answer to that question depends on your take on quantum theory. There are several different quantum theories, some in which there is a wave function that collapses upon measurement, some in which there is no wave function collapse, and that's what I tend to believe in, because it's more parsimonious, that instead of wave function collapsing, depending on your measurement, it's that all measurements exist, and it's you that is entangled with that world that measures it in a certain way, and there are all the other observations occur in other different worlds. So there's many worlds. That's the kind of version I tend to think is true. But again, we don't know. The Schrodinger's cat experiment was just a mental experiment to try to explain why quantum mechanics is crazy, essentially. What is your science view on gender? Gender comes from the brain. So neurobiology is emerging that demonstrates that there are brain phenotypes, that every person has a different brain phenotype that corresponds to their gender identity. And for example, there are brain sexes, right? And there are different types of masculinity, different types of femininity that can influence brains. So what we call a man, right? I believe I'm a man, not because of my genitals, but because of my brain. I have a certain wiring in my brain that gives rise to my gender identity. And in modern, in the modern societal context, I have a certain gender expression. But ultimately, gender is associated with the neurobiology of the brain, the hypothalamus, the cortical thickness, the white matter, the gray matter. And we're finding correlations between trans women and cis women. Their brains are very similar and distinct from cis men. We're finding very, very interesting correlations between brain structure and gender identity, and that is very illuminating. Yeah, so gender is a very thing, and people that are trans are born that way. It's not that they're born trans in the sense that socially they're born that way. It's the sense that their brain is born that way. And if they believe they're a woman, they always believe that. They were always a woman, just like I believe I'm a man, and I always did. It's because of the brain. And it's just that when those types of people grow up into modern society, they get bombarded by people telling them there's something that they don't identify with. And so they align with a different gender than you tell them. And that's why they're transgender. And then there's a spectrum of genders. Under this idea, it makes more sense. It's more intuitive to recognize that there are different genders because there are different brain phenotypes. And it makes far more sense when you understand the science behind it. And this is another realm where science helps us socially. Imagine if every person understood the science behind gender. It would be far, far better for society. We'd be less hateful. We'd be less quick to hate and fight. We'd be more willing to listen and understand. So, on that note, have a good day. And hope you learned something and continue learning and stay curious.